Hello, everyone. Welcome to the second webinar on sampling distributions and statistical inference. This one will talk about ANOVA in the context of the general linear model. So first, a video will be played. I think it's around 1.5 hours that we made recently about this topic. And at the end of the video, I will answer all the questions that you will post on the Q&A section that is located on the toolbar below. So there is a toolbar next to participants below that says Q&A. If you press on that and write any questions that you might have, I will only be responding to written questions, and nobody's allowed to talk. Unfortunately, that's so our videos are homogeneous. So if you have any questions at any point, please write them on the Q&A section, and I will answer at the end of the lecture. So that's pretty much it. Enjoy the webinar, and I hope it's useful to you. We can start the video. So I've read both accounts of ANOVA, which is to present it within the context of a general linear model, and the one who just presents the formulas or the equations behind ANOVA. And I find that presenting ANOVA within the framework of the general linear model makes much more sense. And this is because we are going to talk about residuals, and we need for the ANOVA calculations to be understood, we need to have an understanding of what a residual is, what the residual error is in terms of the linear model, because we will calculate a few types of residual error, the model, the residual error, the total error, and all these can be presented better, in my opinion, if you show a line and you show the data points around that line and show the distance between data points and the line. So that's why I will present the general linear models and give emphasis to ANOVA. So that's the disclaimer. So let's start, because it's gonna take some time. So today I will be talking about the linear models, what they are, the assumptions that the data need to meet before we do any linear model. This, of course, applies to one-way ANOVA as well. We will talk a little bit about the regression, and this is in the context of understanding residual errors. And the TNF statistics that come out of a linear model, a regression or an ANOVA. We will talk about dummy variables and generally how we can insert groups in a linear model. We will talk about the family-wise error and post hoc test, the Bonferroni test. Basically, I'm not going to present anything else today. So let's start. Many models can be written in the general context of a general linear model, and this includes regression, one-way ANOVA, and independent sample t-test. And we will look all of them a little bit, but we will give emphasis on one-way ANOVA. Linear models, basically, it's the idea that we want to describe two variables that are quantitative in nature. They are either on interval or ratio scale, or they are dichotomous. So I need I need one of my at least two variables needs to be in numbers, and the other one also needs to be in numbers or in a binary variable and dichotomous variable. And the linear model wants to draw a line and describe the relationship between these two variables. And we will be looking at this throughout the lecture today. And the general equation behind the linear model is this one. I have one variable, which is the dependent variable, the thing that I'm measuring, and I want to describe it with these terms here. These two terms is the general formula for drawing a straight line. It has a starting point, which is denoted as B0, and it has how you say, a scale. Yeah, so it has a starting point, and then it needs to have some sort of scale, right? Okay, and the idea is that with this line, I can predict the dependent variable. This is done because I want to relate these two variables and make predictions on my dependent variable from the independent variable, even on observations that I don't have, even with numbers that I don't have. So here I have a line that passes through these two variables and some amount of error. This error is basically how wrong is my line, how far away is from the data points, and what the error that this line can make. Okay, so let's see an example here. Here I have 4 observations from 4 people. I took 4 people from the class, and I measured their weight in kilograms and their height in centimeters. And I have 4 people. So each individual has 2 measurements. One measurement is their weight, and one measurement is their height. So this guy here, or this girl, it's around 65 kilograms and in weight and 160 centimeters in height. This person here is 170 centimeters in height and 62 kilograms in weight. I have one person here who is 185 centimeters in height and has a weight of 91 kilograms. And I have another person who is at the top of the scale here, which is 190 centimeters, 190 centimeters in height, and has a weight of 85 kilograms. So each person has 2 measurements, and I want to predict weight. This is the idea here. That's why I have this weight on the y-axis. Is my always on the y-axis is the independent variable, and I have the independent variable on the x-axis here. And the idea is that I want to predict weight in kilograms from height in centimeters. And well, by some mathematics, by some mathematical formulas that we will look throughout the lecture, I draw a line that passes through these data points. And I remind you that these are observations that fall between 2 measurements. Each person here has 2 measurements, and to find their measurements, we need to do this mapping. We need to go from the y-axis to the x-axis, or the other way around. Right, so I draw a line with some mathematical equations that passes through them and can give me a prediction. And this prediction basically means that if I want to know the weight of someone from their height, even though I haven't measured them, I can make a prediction based on this model. So my model here is this line. For example, I don't have anyone who is 180 centimeters tall, but because the line covers this part of this two-dimensional plane, I can make a prediction of what the weight of this person might be. And to do this, I just go up from the height that I am interested, which is 180 at this point, and I find the line, and then I go towards the y-axis. This is done visually anyway. There is a mathematical formula to do this. And from this model, so from this model that is based on the data that I have collected, which is these 4 people, I can make a prediction that someone who is 180 centimeters tall is around 82 kilograms. Their weight is around 82 kilograms. Okay, so what we need to know at this point is that with a line that passes through the data and it's drawn with the previous formula, we can describe the relationship between these 2 variables, independent and independent variable, and make predictions even on data that I don't have. And these predictions are with some amount of error. The amount of error here is how far are my actual observations from the line. Because the line makes a prediction even for the data points that I have. So for someone who is 170 centimeters tall, the line says that they should weigh 70 kilograms. But my data here, the real data, the real measurements, if I go and find someone, if I go and find this person here and weight them, I will see that their weight is less than what the line predicts it is, right? So these data here are off by some amount of kilograms because I'm interested on the dependent variable. The difference between the prediction and the observed values is in the unit of measurement of the dependent variable. Okay, so that's enough for this part of the for the first slide. And what I want you to see here is that there are many types of data, and the line is doing its best to capture the relationship between the 2 variables. But the line, even though it's the best line that can be drawn from this model, sometimes is not good. Some data just can't be described with a line. Okay, let's see a little bit more here what I'm talking about. So I have here my weight and height, and the difference of the observed unit of the observed measurement here from the predicted one is the error. Another term to describe this, it's the residual. It's called the residual or residual error. Residual means what is left. So what is left here from the observation to the model or the line is some weight in kilograms. And every data point is far from the line in some kilograms. And I can make this graph here with the residuals, and I can have an idea how good the model is to describe the data. If the model passes through the data perfectly, every unit of measurements will be 0 kilograms away from the line. So someone who is 160 centimeters in height if the line predicted exactly their weight, there will be 0 kilograms of weight. But for mine data here and this model, the prediction of their weight was around 3.5, almost 4 kilograms below. Because here is a person and here is the line. So this person is 4 kilograms above their predicted weight. This person here is around 6 kilograms below their predicted weight. So the line, the model predicted that they weigh more, and so on. So just to summarize what I've said so far, I have two variables. I have independent and independent variables, which are in numbers. Here I have two quantitative variables. And in order to describe them, I draw a line with some mathematical formulas that tries to pass through them. But even though it passes through them, each observation is some degrees of measurement away from it. And this is my error. How far away is each data point from the line is the error of the model. The model didn't do so well in some cases, but did well in some other cases. And this is what we are interested to know. If the model is good, a general term to describe the goodness of fit or other characteristics of the model that I'm interested in is called bias. So generally, we want to know if the model is far from the truth. The model here is the line, and the truth is our real observations, what we've seen, what we've measured in actual measurements from our participants. When the model is biased, when some characteristics of the model that we are interested in are far from the truth, our observations, we say that there is more unsystematic variation than systematic. So there are other things that play a role in the description of the independent variable other than what I've measured. So not the independent variable. And because I haven't measured them, or in experimentation, there is no systematic manipulation of these variables, we say that there is unsystematic variation that affects the dependent variable. Okay, so a lot of terminology here, but we go back to familiar territory because you know what this is, or you should know what this is. This is the standard error of the mean. The standard error of the mean is a measure of bias. It tells us how far our sample mean is from the population mean. So this is a mathematical formula that can tell us something about the mean. The mean sometimes is a model, but not today, or at least not now. So this standard error is a measure of bias because it tells us how far our sample mean is from the population. And it's derived from this calculation. Another measure of bias is the confidence interval that I'm not gonna talk a lot about today, but I think you should know from previous lectures in these webinars in this series. But the confidence interval, basically half of it is the formula, is the equation of the standard error. So this part here is the standard error, multiplied by a confidence level, where it usually is 0.95 and means 95% confidence interval. And then the answer, the product of this calculation here is two numbers, and I want one that is above the mean and one that is below the mean. And it gives a range of values that you can be 95% certain it contains a population. Anyway, these two things here are a measure of, can be considered as a measure of bias. So when I run linear models, I get many statistics and parameters that describe the model. Here I show you some of this. Then this is descriptive at this point. We will look at this further as we move along. Here I run a linear model with a question of borderline disorder. I think this is a borderline scale. This is a measurement of borderline. So this is question 3 of a borderline questionnaire to the total borderline score of a sample of, I think, 70 women here in Cyprus. Anyway, and I expect some relationship in this, but not with this question. And I get here a beta coefficient, which is one part of the equation that I showed you previously. I get a standard error. You know what the standard error is, but in this point, this is a standard error of the beta coefficient, not of the mean. I get a t-statistic. You know what a t-statistic is. I get a p-value. You know what a p-value is. And confidence, two numbers here that are the 95% confidence interval, the lower bound and the upper bound. And anyway, I'm gonna describe this later, but the point here is that biases can be seen, or things that show that the model is affected by biases can be seen in many of the statistics and parameters. It can be seen in the beta coefficients or the effect sizes. And they can be seen in the t statistics or the f statistics if we have them, and the p-values. And where my model is far from the truth, I can identify what is wrong with it. So if test statistics are far from the truth, like t-tests and p-values and f-tests, there are probably some issues in my model when I want to generalize it to the population, to samples that I have not yet measured. But if there are issues with the parameter estimates, then I have within sample problem. So the way I predict the outcome variable might not be the best. And depending on your question and the applications of the model, you can decide which one is you need to fix, or the way to fix it. But we will look at this perhaps later on. So some ways that models can get biased is due to the nature of their own data. So the data need to fill some characteristics before we try to describe them with a linear model. And these characteristics are generally called assumptions. And we want to see if these assumptions are met or if they are violated. Generally, because we are talking about linear models, there are a set of assumptions that you need to check your data if these assumptions are met in the data for all the linear models. So either if you are running regression, if you're running ANOVA, if you're running t-tests, these assumptions should be applied to the data. And this is for all the parametric statistics, because they are all based on the normal distribution as we have spoke about before. The first and most important assumption is that of linearity and additivity. Basically, linearity means that a line should be able to describe the data, and it makes sense to check this assumption first, but there are no tests that specifically test this assumption. You can only look at your data visually and have an educated guess of whether a line can describe them, or if you need other types of models like polynomial or I don't know, something else. And additivity means that in cases that you have more than one independent variable, and if you have a large data set with many variables, and you are at that point you will be doing multiple regression or other things that we are not interested in today. As you enter variables into the model, they should have an additive effect. Then the combined effect of the predictors can be best described by adding them together. This means that the fit of the model or other indices that the model is not biased should increase as you add variables. So basically, you don't go around and whatever you think, you measure it and you throw it in the model. This is not what you should be doing. Every time a variable is added or before you run any model and you are thinking which variables to add, you need to make sure that it's best to add them than not to add them all together, basically. So to avoid this, you need to have a strong theoretical background and good experimental design, basically. Many things in the data should be normally distributed. Their own data, so the dependent variable needs to be normally distributed. The independent variable needs to be normally distributed, and the errors also, so the residuals, how far away from the line each data point is, also needs to be normally distributed. This is because you want to have most observations to be the same distance from the model. You want the model to do the same job in all observations. You don't. That's what basically normally distributed residuals means. Sorry. Outliers sometimes affect normal distribution, so you need to check for outliers. And if you don't have normal distributions, you will not get good parameter estimates like the beta coefficient. Because nowadays we have like big data consortia, and it's not uncommon to have a lot of data rather than small samples. And we know that the central limit theorem applies. The bigger the sample you have, the less you need to worry about normality. The way to examine if your data are normally distributed is with PP plots or with other specialized tests like the Shapiro-Wilk that test specific null hypothesis. And you need to know which null hypothesis is tested in each statistical test that you are performing in order to interpret the p-value correctly. So another important assumption is the assumption of independence. That basically the definition of this is that the residuals for every observed value must not be related with the residuals of any other observed value. And this basically means that observations must be independent. If there is some kind of relationship between your observations, then you should not be using a linear model. And here I have a set of data that are not that don't that are not independent. So this assumption is not met in this data. Is, let's say, for example, I collect data from these participants here, but these participants belong to specific neighborhoods or states, or that these states belong to some regions. So these participants here are all related in some sense because they live nearby, and these sets of observations are also related because they live in the same region, and this is the same. And depending on your research question and experimental design that you are following, you need to take this into account. Because if this applies to the measurements or your data, you need to run multi-level models or hierarchical models of some sort, or not a linear model anyway. You can avoid this by good research design and by basically understanding your data very well. Another assumption that applies to all linear model is that of homoscedasticity or homogeneity of variance. This is the same thing. It has two names, as most things in statistics, just to make things confusing. And this assumption basically says that the same outcome variance, so outcome here is independent variable, the same outcome variance across all level of the independent variable or the predictor. If this assumption is violated, again, you don't get the best parameter estimates, which are the beta coefficients in linear models. But there are ways around it. So these are not so, let's say, for example, you can do weighted least squares instead of ordinary least squares if this assumption is violated. What this means basically is that if I have groups, if I have groups inside the linear model, let's say in two groups, let's say tall and short people, or autism and control, or something, then the variance of the outcome variable needs to be roughly the same between these groups. If I have a quantitative variable in numbers, then the variance between each observation of the independent variable needs to be roughly the same. And there are tests for this. It's the Levin's test that tests the null hypothesis that the variance in equal groups, so the number of individuals in each group is the same. There is another robust test for the same use, the Brown-Forsyth test that uses the median instead of the mean, and it's more robust, again, non-normal data. So it basically cannot be affected by outliers because we know that the median is not affected by outliers. But you can also make graphs of the errors and the prediction. So before, at the beginning, we saw that the errors is how far each observation of the independent variable is from the line, from the predicted value of the dependent variable is from the predicted value of the independent. And we can look for this assumption graphically. Here I have a model, which is basically the predicted values of revenue against the actual values of revenue, and the distance the actual values have from the predicted values in a standardized manner. So these are some units of measurement. Here they are kind of z-scored. And when this happens, I am looking for a pattern here. And if there is no pattern, that means that the assumption is met. So there is homogeneity of variance. If there is a pattern to this like this, then means that the assumption is not met. And the way this is interpreted is that as I move along the x axis, I get vastly indifferent variance at some part of my data and distribution. So anyway, just to close this section here. So the last important assumption is that of homogeneity to variance. There are specialized tests for it that test for specific null hypotheses with their p-values, the Levin's test and the Brown-Forsyth test. But you can also look for this assumption graphically by plotting the residuals against the model. And you can have a standardized version of this graph. And if there is no pattern, then it means that it's likely that this assumption is met. But if there is some pattern like this or the other way, more, let's say, rare, but if there is some pattern on this graph, it means that as we move along the x-axis, the residuals are vastly different from previous measure. Right, okay, so if all these assumptions are met, we can move forward and draw a line. We saw before that we want to predict the dependent variable by drawing a line that has a starting point and a slope, not a scale, a slope. I was forgetting this word, and a slope and some error. So we saw what the error is how far is each observation from the line, and we saw what the dependent variable is our measure. And the remaining thing is this thing here, is where to start on the y-axis to have the line and its slope. So how, what slope this line should have in, let's say, in degrees or some unit of measurement that it's a unit of measurement of the independent variable. And I need to find these two things here. So the regression, it's the main linear model. It quantifies the idea that we can predict a number from other numbers. And for example, we can predict a person's score on a sexuality questionnaire from their score on an identity questionnaire. We can quantify the predictive ability of one variable over another, and this is basically quantifying their relationship. We can use this in psychology, but also in other fields to intervene in dysfunctional behaviors. For example, if I know that I can predict a person's sexuality from an identity questionnaire, I can, let's say, prepare an intervention or some sort. I can help make policies and generally make our life better. We can have positive and negative relationships as in correlation, if you know what a correlation is. As I told you many times by now, you know that the regression equation is the same as the equation from a straight line, for a straight line without the error. And linear models draw a line in a space with dimensions equal to the variables they contain. We are only looking at two variables, one dependent and one independent, so we have two dimensions. that we can visualize easily, one X and one Y. The line passes through the two-dimensional space, passing through the observations that fall in this plane. So each observation, remember, has two measurements, one which is our dependent measurement and one that is our independent measurement. So this line passes this two-dimensional plane, and it tells us that if I have any number on the variable on the x-axis, I would have such a number on the variable on the y-axis, even numbers that I haven't really observed. The error, as we've seen so far, is important because it tells us how wrong or correct, depending on if you are a positive person or a negative person, tells us how wrong or how correct the model is. Every observation has an error. Every observation is far or close to the line. And the model is doing better in some observations than in others. It passes closer to them, and passing close to an observation minimizes the error. Passing far from an observation, it maximizes the error. And now I will be talking about penguins, or basically I found data from penguins online, and they are really good for regression. So that's why I'm not an expert. But here my variables are body mass in grams and flipper length. Flipper is some part of the body of the penguin, measured in millimeters. Right, so, and I want to predict the penguin's body mass in grams from their flipper length. These measurements are in different units of measurements, but that's okay for regression, it doesn't matter. Here we can see that visually we have an idea that a line can describe this data. So if I draw a line starting from the y-axis here and with a certain slope, I can pass through the data and through all the observations here. So the first assumption is applied. I have only two variables, so I'm not concerned about additivity. I'm not showing you the other assumptions test here, but that will make a really long webinar. Anyway, back to my interest here, which is the residuals. And I want to know if this line is good or if this line is bad. So I calculate the residuals. Every observation here is far from the line in some sense. And when I want to know how far each observation is from the line, then I do this residual plot here. And I find that every observation is some amount of grams away from their predicted weight, their predicted body mass. Okay. And I see that I have different error terms as I move along the x-axis. So when I am around penguins that have a flipper length of 230 millimeters, I see that I have more homogeneous residuals here. But if I am somewhere here or here, I have a bigger spread of residuals. Anyway, so let's get some estimates from this model. Let's solve the equation, basically. Sorry, I get, so let's just solve the equation here. So this is my equation that I want to solve. Let's change the symbols here. So my independent variable is my body mass, G, for every penguin. And I want to know where to start drawing the line. This is called the intercept. and is this number here, as the model is saying here, intercept has a beta 0 coefficient of this number, and my B1 coefficient is this one, which is this number here. And I have some amount of error. This is the standard error of the beta coefficient from this part of the model. And this basically means that if I had a penguin with a flipper length of 0, which is impossible to measure because no such penguin exists, I will have a body mass of negative 5,872 grams. Right, and for every gram, for every millimeter of flipper length that I get, the line increases, the body mass increases by this amount of grams. So if I start from 0 and count all the way to my first observation, which is around 160 millimeters of flipper length, I will do 160 times this number. And for every observation that I have, it can be 1.5 grams of either above or below. So this is the error. Okay, so let's recap. So because I don't have a penguin with a flipper length of 0 millimeters, I am forced to start drawing the line from my lowest observation of flipper length, which is, I think, around 160 millimeters of flipper length. So in order to find what body mass this penguin has, I need to do 160, which is my first observation here, times B1, which is the slope. And the result should be something around here. And every time I move along this plane, I have 1.5 grams of error. Right. Yes. So how do I get these numbers here? I get these numbers by a method called ordinary least squares. An ordinary least squares is a method that tries to minimize the errors. It tries to minimize the errors. And the way it does this is by some computational method that draws many lines and calculates a sort of error that is the sum of all residuals. And the line that has the lowest amount of residual error, it's the one that is finally presented as the model. So the computational method that is trying to minimize the error. It's basically squaring the residuals to avoid negative values and then summing them to produce one value. And this is the square error. Ordinary least squares is a sensible method. By using square residuals, you can avoid positive and negative residuals canceling each other out and find a regression line that is as close to the observed data points. It's a good predictor and it has asymmetric properties. For example, it passes through the sample means of X and Y every time. the mean of the predicted y values is equal to the mean value of the actual y, and the mean of the residuals is always 0. And because we saw from our normal distributions webinar that symmetry is something that it's really it's something that statisticians really like, and it has the symmetric properties. It means it's good. So I have these variables here, and I want to know if the model is good, if my line is good, if I have a lot of error, or if I am far from the truth here. And I want to sum the residuals and do the same with these ordinary least square methods, because even though the best even though the line that I get back is the best line possible, this doesn't make the line a good model. The best line might be a bad model. Okay, so I still want to know some information about the errors. I still want to know if how far or how close the model is from the actual observation. And summing the square residuals will give us one number to assess the model. We want to assess how far the predicted values are from the observed, how well the line fits the data. As I have told you many times, the residuals is the difference that the model has, so the predicted values from the model from the observed data. And in order to get a number that it's called the sum of square residuals, I need to sum all the errors. If this number is small, then the line fits in that well, and the predicted values are not far from the observed values. Residuals are squared to eliminate negative values and avoiding canceling each other out, as I told you many times. But in the spirit of the null hypothesis significance testing, I need to compare this number with some baseline. I need to have, if I am allowed to use this word, a null model, a null model, to compare it to the line. And this is called the sum of squares total, which is basically the mean. So I want to calculate how far each data point is from the mean. And I treat the mean as a model in this situation. Here, this is the mean of the body mass in grams here. And as I move along the x-axis, the mean is not a good model, because if I have one flipper length here, I predict a body mass of the mean. If I have another flipper length here, I predict a body mass of the mean, and the same and the same. So the mean is not a good model, but it's a good baseline model. So I want to know if the line is better than the mean, if my linear model is better than the mean. And in order to assess this, I need to calculate the residual error of my observations from the mean. So I do this again, and I calculate how far is each data point from the mean. And this, as I told you, it's called sum of squares total. And in order to compare these two, I need to subtract the sum of squares residuals, which is the error of the model, from the sum of squares total, which is the error from the mean as model. And I get a number which is basically the sum of squared model. It tells us the reduction of inaccuracy. in the spirit of Ronald Fisher, which everything is a little bit, you know, transverse. So it shows us the reduction of inaccuracy, the sum of squares model. And if I want to get a ratio of how good my model is at improving the fit based on, in comparison to the mean as model, I get this I do this calculation here, which is the sum square model, which is the reduction of accuracy, over the sum of squares total, which is the mean as model. I get this number here, which is an R2 square. R2 square is very important parameter when assessing linear models. It tells us the proportion of improvement by using the model instead of the mean. And we treat it as showing the amount of variance, the percent amount of variance that I can explain in the independent variable. If we take the square root of the R square, we get a Pearson R between two variables. If I have a simple linear regression as in this situation, and there is another thing that it's called the adjusted R square, which is the R square divided by the number of variables here, and it shows parsimony. But we are not interested in this thing now. Anyway, so to recap here, I want to assess how well the model is, how far is each observed data point is from the model, and I also want to assess how far is each observed data point from the mean as model. And then I either get a proportion of the reduction of accuracy to the mean as model. I get a proportion of improvement, which is a general estimate of the fit of the model. And we treat it as showing how much variance is explained. In my data here, the R2 square is 0.76. And it means that this variable, the independent variable, which is flipped length, can explain 76% of variance of the body mass G, which is in grams. Okay. This sounds good, but what is the chance that I get this result based if the null hypothesis is true? And the null hypothesis in this situation is that there is no relationship, there is no predictive relationship between flipper length and body mass in grams of penguins, right? So I need to get some test statistics in order to answer this question. And in order to do this, I need again to do something with the errors, with the residual errors. So sum of squares in some form are used to give us test statistics like the T statistic and the F statistic. The T statistics show us as the amount of systematic variance relative to unsystematic. The model compared to the error. To get a test statistic, we use the sum of squares of the model and the error. So remember, the SSR is the amount of error around the model, and SSM is SSR when it's subtracted from SST, which is the mean of model. But I also need to use something that's called the degrees of freedom that was introduced previously. So I have different kinds of degrees of freedom, as I told you. And here I have the degrees of freedom that come from the number of variables that I have in the model. I denote it as K here. You might find it different symbols. And I have the degrees of freedom that are related to the observations. These are also called the numerator and the denominator degrees of freedom, but everything has 2 or 3 names. Anyway, the idea is that to get a test statistics, I need to use the degrees of freedom, and I need to calculate the mean of sum of squares. So to transform a sum to a mean, I need to divide it with the number of something, the number of observations, the number of variables, and this is the case here. So I get a sum of square model divided by one of my degrees of freedom. And I want a sum of square residuals, a mean sum of square residuals, that is divided by the number of observation minus the number of the degrees of freedom of the number of observation minus the degrees of freedom from the predictive variables minus one. To get an F statistic, which is how much is the systematic variance over the unsystematic, I do this calculation here, where is the mean sum of squares divided or over mean sum of squares error, residual. And this F has an associated probability distribution in which we can get p-values. This is also used to calculate the significance of the R2 square that we showed before. To get a test statistic, to understand the T statistic now, so any predictor in a linear model has a beta coefficient. Here we only have one predictor, and its coefficient is denoted as beta 1, is the slope of the line. If we have more, we would say B2, B3, B4, B, etc. If the predictor is completely useless, then beta coefficient will be 0. That's why if there is 0 in the confidence interval of the beta coefficient, we accept that a possible value for that predictor can be 0. Therefore, the null hypothesis is that the t-test is examining is that if a predictor is good, it should have an effect different from 0. A t-statistic test for that hypothesis and gives us a p-value to accept or reject the null hypothesis. And the t-statistic test is also based on the idea of explained versus unexplained variance for every predictor. If you remember the computations of the one sample t-test and the independent sample t-test, they had a standard error associated with them. So the standard error of the beta coefficient in this case is how different is the beta coefficient across samples that I have not measured. And in order to get a t-statistic, I get a t observed, then a t expected divided or over the standard error of the b. And because the null hypothesis is that the b expected is 0, so because this is 0 or under this null hypothesis, I don't take it into account, and I go straight to have a b observed, which is the beta coefficient that I get from each variable, divided by the standard error of the beta for each variable. This is the equation of the standard error of the beta in linear models. I'm not gonna go into detail here, but it's basically the observed value, each value of the dependent variable minus the predictor, the predicted value of the dependent variable, sum squared and the sum. And here is each observation of the x variable minus the mean of the independent variable square and the sum. And then this equation here. Okay, so let's brief. We saw many things. And let's go and do some ANOVA. Or basically what we do when we have groups in a linear model. So, yeah, okay. If I have groups, that means that one variable of the two that I am looking at this point will only have some labels that describe the group. For example, here I have two variables, which is the grades of a school on the first semester, here. I have 3 semesters, G1, G2, G3 here, and 2 schools. I think these are schools from the USA, but I don't remember. And okay. And here I have, so I have 2 variables, which one is a quantitative variable and one is a binary variable. So each individual here will have 2 measurements. One is their semester grade, and one is the school they belong to. And to describe this data, I do a box plot here. The line is the median, and the dot is the mean. And first, second, and third quartiles here. Okay, and I see some differences. I can see that this group here has this school here, the GP school has greater mean and median grades in all 3 semesters. And generally, I get a sense of the data. But the point here is that one of the variables is described, it has the measurement is a binary measurement. It's either that school or the other school. And when I have 2 groups, I have, as I told you, a binary or a dichotomous variable. That's the same thing to describe a grouping variable with 2 levels. And I need to get this variable inside this model. And we are trying, basically what is happening here is that we are trying to predict the independent variable based on the group that each observation belongs to. For example, if I want to predict IQ in measurements that were done in individuals with a diagnosis of autism and control group, I will need to include the variable diagnosis inside the model. But diagnosis it's a variable that has 2 levels because it's a binary or dichotomous variable. It's a variable that has these 2 names. Each person is either under this name or under this name. The beta coefficient will predict IQ from group membership, autism or control. But what is happening is that it will show differences and it will not make predictions in this case. And the t-test will show us whether the difference between means is different from 0. Remember that the t-test in linear models tells us whether the variable is better at predicting the model than non-predicting. When the independent variable is dichotomous, t-test tells us whether the difference between groups is bigger than 0. And we will look at this later. The first assumption of the t-test that we saw at the other time was that we need to work with numbers. We cannot write mathematically autism and control. So the control group should get a unique number and the experimental group another. The control group usually gets a number of 0 and the experimental group gets a number of 1. That's why the name binary, basically. If I have more than one group, I can do dummy variables, which is this idea. So if I have one variable here with, it's called gender and has male, female, male, female, I can get one variable that has 1 for one group and 0 from the other. These variables are mirroring each other. So whatever has 1 here, I can use only 1 and it's fine because each individual has either 1 or 0. If I have more than 2 levels in my grouping variable, I get something like this. And for each dummy variable, so if this person here, my first observation, this is another kind of data set that shows mother's job, and it's from this data set with the schools. And shows for every student what job their mother is doing, if they're staying at home, if they're working at health, if they're working at services, if they're teacher, or if they're other. So this person here, their mother works at home. So in this dummy variable, their mother gets a number 1, but in all other dummy variables gets a number 0. So each dummy variable shows group membership for a specific level. And because linear models can only work with interval ratio or dichotomous variables, if I have more than one group in my grouping variables, I do dummy variables, and so I have many binary variables inside the linear model. Okay, so in dichotomous variables, it matters which number will be coded as 0, because 0 is our B1, it's our observation, it's our first observation. The best thing a linear model can do when working with dichotomous variables is to go through the mean. And I will demonstrate this now. So I have a group here, which is one school, and one here, which is another school. And the ordinary least square path, so the path of the line that minimizes the error between two groups, is the mean of the groups. Okay, so if I have a line that will start at some part of the dependent variable, it will be the mean of the group that is coded as 0, and it will go to the mean of the other grouping variable that is coded as 1. That's the least square error path. And the beta coefficient for each of these model is the difference between the means. Because to go from that point to that point in a straight line, you will need to find the difference between these two means. The intercept, as I told you before, is the mean of the group that is coded as 0. For example, if I have individuals diagnosed with autism and individuals in control group individuals, the control group will be coded as 0, and the line will start from their mean IQ, which is 100. And let's say the mean IQ of this sample of individuals with autism is 70, or the difference will be minus 30. So to find the line, to find the mean of the other group, we'll need to go 30 IQ points below this mean. So the beta coefficient will be, the B1 coefficient will be minus 30, and the beta 0 coefficient will be 100. So imagine what would happen if I have many groups. And this is what we will be talking about now. So comparing more than two means in the linear model. So each beta now will be the difference between two means. Here, we can examine the fit of the linear model to the data with the F-test, because it will tell us if there are any differences between our means. And then we will look at each dummy variable. Remember that we said that the F-test is the systematic variance over the unsystematic variance. If there is systematic variance, it means that our groups are meaningfully slicing the dependent variable. So we can examine the fit of the linear model with the F-test, because it will tell us if there are any differences between our means. And then we will look at each dummy variable separately to see if the differences between the mean of each variable and the mean of the group coded as 0 is significant. Okay, so we run a model with this. We have 5 group. Here I have the, basically, let's describe the data first. I don't know what time it is. Let's describe the data first. I have 5 types of mother's job here: at home, health, other services, and teacher. And I have the first semester grades of a school. And I want to know if the students' grade are significantly different depending on the job of their mother. And in order how to do this, I will do dummy variables as I have here. So each dichotomous variable, each binary variable here shows group membership of a specific job. So these guys here, their mother works at home. These guys here, their mother works at service, right? And each person, each participant has an associated first semester grade. Okay, the way this is done is that we leave one variable out, one dummy variable out, and this is the control group. This is in beta 0 because the variable we left out will be 0 in all other dummy variables because it will not be represented. Anyway, so we leave one dummy variable out, and this is our intercept. This is our beta 0, and we have a beta coefficient for each one of the other variables. So, and I get this model here. I get this model estimates here. And as I told you before, the beta 0, the intercept, we have to start drawing the line is the mean of the control group, or the group that is coded as 0, the group that is left outside. In this case, the mean student grade for the first semester for the kids that their mother works at other is 11.2. And the difference of the mean between the other types of mother job means is this. So the difference of the means between these two categories is the beta coefficient of this job at home. The students that their mother works at health services has a difference in mean of the magnitude of 1.1 from this. And we can see this here. So health has a greater mean from the other mother job, and so on. And each variable here has an associated t-test. And this t-test tells us if the difference between the means of the control group and each of these groups here is significant. If this difference was produced by the null hypothesis, what is the chance that this difference is produced by the null hypothesis that there is no difference? And an associated p-value. And each mean has a standard error. So this is the same linear model that we saw before from regression, but now it's a difference of each group mean with the mean of the control group of the intercept, with the beta 0. And it took me ages to draw this graph here. So here I have the grand mean, which is the pink line. So it's a mean of all students in the first semester without taking into account their mother's job. If we take into account the mother's job, we see that each group here, each mother's job is related, has some difference with from the pink line, and some difference from the control group mean, which is the mother's other job. Okay, so how am I going to write this down in a linear model fashion? I want to predict first semester grades from 5 groups. One of them is the control group, and every other group is compared to it, and I have some amount of error. Um, and each of these beta coefficient, other than the B0, tells us the difference between the control group. So B1 is the difference of the mean of at home from the mean of other. B2 is the difference of the mean of health with the mean of other, and so on, as I explained. So when we compare many groups inside a linear model, the beta coefficient represents the mean differences with a group that is a control group or the group that is left out when you do dummy variables. The mean differences with the intercept, basically. The t-statistics is similar to one sample t-test. And here we compare each sample's mean with the mean of the control group or the group that is left out or the intercept. It tests whether they come from different populations significantly. The F statistics now for the linear model that we haven't seen tests model fit. It says whether there are differences somewhere within the groups, but it doesn't tell us where these differences are, only that they exist. As we have already seen, the F test tells us if there are differences between our groups. It does that generally. It doesn't tell us where there are differences, only that they exist and that they are important if the p-value is less than the alpha level. If the F statistic is not significant, then it means that our group do not discriminate. They are the same. So it doesn't matter if I have groups because their mean will be the same with the overall mean. It doesn't matter if I add up the independent variable in different groups, their means will be the same with the overall mean, the pink line, as I showed you before. So the null hypothesis that the F test is testing is that the means of the groups are the same. And this means that the mean of the group of B0 is the same with the group mean of B1 and so on. So if the null hypothesis is true, then all the beta coefficients will be 0 or close to 0 because there will be no mean differences with the with each other, with the intercept and with each other. The alternative hypothesis tells us that there are differences somewhere, and it's mathematically written, and this is funny because you cannot write it as known difference because it will mean that there are known differences between each comparison. It's written like this. The alternative hypothesis is that the mean of one group and another group are not the same, but it doesn't specify where these differences are. And I remind you here that to get an F statistic, we need to get the mean sum of squares for the model over the mean sum of squares of the residual. The model compared to the error, or the ratio of explained to unexplained variance. Okay, so you are all here for ANOVA. Let's talk about ANOVA. And it's pretty much what we are already discussing, is that we want to find the proportion of variance, then see how much of it the model can explain. Is it meaningful to cut up the independent variable into groups? If the total error is small, then the model is good. We will do all this with sum of squares, so we will calculate different types of error and then square it up, sum it up, divide it with the degrees of freedom and find some number. This number will tell us how far our observations are from the model and different kinds of models. So the first step is to find the whole variance. That's what it's called, the sum of square total. We have seen it before, and we want from each observation, so without taking into account any of this, every observation here is we subtract from it the grand mean, so the mean of the dependent variable, we square it, and then we sum it up. And this is the same as using the variance of the dependent variable. It's the same equation. And the variance in this situation tells us how far our observations are from the pink line. Now, our observations here is observations, not means. Sorry, this is wrong. In our sample, the variance of the dependent variable is this number here. And the sum of square total in this situation shows us the between group variance definitions of it's a measurement, and the variance means you should know this, but variance mean is a measurement of the spread between numbers in a data. Okay, another error that I need to calculate is the sum of square model. How much of this variation can the model explain? How much of this number, so I have the variance of the independent variable, is this number there, can the model explain? Now we use the means of different groups because we were using dummy variables. So the model are the group means. The model is the line that passes through the means. We want to see how far from the grand mean, the pink line, are the group means. We multiply the difference of each group mean with the grand mean by the n of the groups. We do this for all groups. So I get, in order to calculate the sum of square model in this situation here, I get for each group, I get the mean, and I subtract from it the grand mean, which is the mean of the independent variable. I square that, multiply by the number of groups. And when I do this for all groups, I sum it up. In our data, the sum of square model is this number here, 275.1. So far, we know that there are 4,883 units of variance to explain, and we explain only 275. And the sum of square residual, which is the error of the model, tells us how many units of variance the model does not explain. And to get this, not surprisingly, we subtract from the sum square total the sum square model. And in this situation, is 4,883 units of variance that are in my dependent variable. Then groups explain 275, so there is 4,608 units of variance due to error or due to unsystematic variation. We can get this number by summing up the variances of the group as well. The variances of each group total to this. So SSR is our within group variability. Is a within group variable. To get an F statistics from this sum of square, we need to divide some things with some degrees of freedom. As you remember, we have summations, and to go from summations to averages, we need to divide with something. And this something is always the degrees of freedom. So we have two types of degrees of freedom. And degrees of freedom of the model, which is how many groups I have, -1, and then degrees of freedom of the residual, with the sample degrees of freedom minus the degrees of freedom of the model. This number here. So so this is the mathematical terminology. Sum of squares are sums, so they depend on the sample size. To eliminate this bias that they depend on the sample size, we calculate an average and divide the sum of squares with the degrees of freedom. Okay. So we have mean of square model, which is the sum of squared model divided by over the increase of freedom of the model, and this number here, and we have the mean of squared residual, which is this number. And I get basically the average amount of variation explained by the model, and the average, so this is the between group variance and the within group variance. The average amount of variation explained by the model, and the average amount of unsystematic variation that is not accounted by them. And when I get the mean sum of square model over the mean sum of square residual, I get an F statistic. This is the between group variance over the within group variance. If I have tight groups that don't that have small variation and show differences only between groups, then I get a large F. And this F basically is the ratio of the experimental effect to over a non-experimental factor that I have not measured. In our case, so under our example here, the F is the ratio of mother's jobs to no effect of mother's jobs on the grades of the first semester. The effect of mother's jobs is 9 times larger than no effect. The means of and this basically means that the means of the mother's jobs groups are different from the mean of the dependent ones. But is it significant? What is the probability to get such an F value if the hypothesis is true? And you get this familiar critical table. Here I have 2 degrees of freedom to associate my F statistic with. This is the numerator degrees of freedom, which is the one that is coming from the number of groups that I have. And then denominator, which is that comes from the sample. In our case, which is 9 something, I have 4 groups. And since here I don't have 6, I have 640 something individuals, but I don't have this number here. So I go to the previous one, which is 120. And because the F statistic is greater than this critical value here, it can be derived if the null hypothesis is true less than 5% of the time. I can check for 1% and still holds. So it's p-value less than 0.001. There is a recap of the assumptions of ANOVA, normality of observations within groups, homogeneity of variance, if assumptions are violated, but also for a robust way to interpret. There are newer ANOVAs, basically. It's the Brown-Forsyth F statistic, which is one that uses mean, and the Welsh F that does some weighting on the groups. If you have an equal group sizes, you use that one. It has some weight parameter. And there is also a non-parametric ANOVA, the Kruskal value. So why not run a t-test between all my groups and bother with ANOVA? Why not just run like t-test between all possible groups? And this is because of the family-wise error. Basically, the alpha level is 1 minus my confidence level here, which is 95%. And this results to 5% chance of observing the test statistic if the null hypothesis is true. If I perform t-tests between 5 pairs of mother jobs, for example, let's say, for G1, then I increase the alpha level. This is the probability of obtaining a result if the null hypothesis was not true is this number here that is derived from multiplying my confidence level. So if I do 0.95 times 0.95, I get this number. So the alpha level in the whole experiment under all this is 0.75 subtracted from 1. So the alpha level is increased. And this is because all these mother jobs are under one variable, which is mother job. I don't have separate mother's job at home and mother's job at health and mother's job at services. This is one measurement. And if I, in quotations, cheat and do t-statistics between t-tests between all of these, it's like I don't take into account their uniformity, that this is one measurement. But family-wise error does not exist if you run one test, and this is one ANOVA test. One ANOVA test only has one confidence level and one alpha level, and takes into consideration all possible combinations of group comparisons and their variance and their residual error. So alpha level is the same. The result of ANOVA is an F-test that tells me that there is difference somewhere. However, I still need to find where. To do this, I still need to do many t-tests. But I correct the p-value. The p-value is corrected by the Bonferroni method. SPSS, that I think is what you are using, has 18 different ways to correct for family-wise error. The Bonferroni method basically divides the alpha level by the number of tests. If I have 5 mother jobs, I will do my alpha level divided by 5. I have a wrong number here. If I have 9 mother jobs, I will get this alpha level. So when you have more than 2 groups, it's better to do ANOVA in order to combat family-wise error. To do this, you need to transfer the data to dummy variables and leave the control group out of the model. If the result is large F, so above 1, and has an associated p-value less than the alpha level, then there are differences between your groups on the dependent variable. The null hypothesis that says that all group means are the same is rejected. The alternative hypothesis that says that at least one pair of means different is adopted. Then you need to find where. To do this, you run t-tests between groups, but you need to correct the alpha level. You can correct it with the Bonferroni method, with the p-value divided by the number of groups. Why not lower the alpha level and do many t-tests from the beginning? Because some aspects of variance and error will be left unaccountable. This is because there is only one variable within groups and not separate group entities. Refer to the previous calculations to see how many residual errors there are and need to be calculated from a combination of group variances and residuals. And here I remind you that the statistic, which is the essence of ANOVA, shows the between group variance over the within group variance. If the variance within groups is more less than that of the between groups, we'll have a great F value. So thank you.
Perfect. I hope everybody enjoyed the main seminar. We're now going to proceed to the questions and answers section. So if anybody has any questions that they haven't yet posted in the Q&A, you will find it located at the bottom of your Zoom controls on the left-hand side. It's the 2 speech bubbles next to each other where it says Q&A. Just post your questions in there and we'll get to them sequentially. So, Dr. Dragoshis, let's begin with the first questions. Where can I get the video? Whom can I contact? The videos will be edited and they'll be uploaded onto the VLE in the Student Help Center, but this may take up to a month. So you'll find them on the Student Help Center in the VLE. Next question. Great explanation for us to understand related normal distribution and bias. How does the urgent importance bias potentially affect our interpretation of data, especially when we assume that our data follows a normal distribution? So that's the first question. Then it has a follow-on, but let's start with that. how does the urgent importance bias potentially affect our interpretation of data, especially when we assume that our data follows a normal distribution?
Yeah, thank you for the question, Tris, I think.
No. Don't mention names, please.
Oh, sorry. Sorry, my mistake. So thank you for the question. Cognitive biases are not the topic that we are discussing today, and I'm not even sure what's the urgent importance bias. I guess it's some kind of a cognitive bias, and it will be best answered in another type of cognitive psychology related webinars. I'm not in any way expert, and I cannot answer this question. About the second part of the question, could focusing too much on urgent but potentially atypical data points lead us to overlook significant trends or patterns that are evident in the overall distribution of our data? Focus now, some of these words are not statistically related. For example, focusing too much. I think you have some issues with your time management if you think you are focusing too much on some data points. But just to make, I want to make a distinction clear that might help you here. So we're talking about normal distribution. We talk about one variable and its frequency, how the frequency of one variable is presented. So we're talking about one variable there. And we count how many times we observe each data point. And if most observations are around the mean, we have a normal distribution or an approximately normal distribution in some sense. If we want to look at trends, if we are looking for trends in our data, we will inevitably look at more than one variable. We will look at two variables and see in a scatter plot format if there are any trends between these two, let's say salary and different kinds of jobs. Let's say, for example, grades across different classrooms or across different different modules or stuff like that. So trends, we look for trends mostly if we look at two variables together. But here in this and in the previous webinar, we were talking about the normal distribution, which is a frequency distribution that on only one variable. Atypical data in a frequency distribution can only be considered the outliers. As I've mentioned, I think in the previous webinar, it's really worth to have a specific webinar on outliers and see examples and think about ideas on how to treat outliers, because it's not as easy to decide if an outlier is an outlier or there are other types, other concepts that are related, like influential cases and stuff like that. So focusing too much on any type of data, either atypical or typical, is always a good idea. And to look at trends, you need to look at two different variables. And when we look at two different variables, here we are discussing about how to describe them using a linear model.
Okay. The next question is, will the presentation slides be shared? A decision hasn't been taken on this yet. Very often they're not shared, but I do think that for this particular webinar series, it's important to have the notes as well as the recording. So provided none of the presenters object to their slides being shared, which I don't think anybody will, we will also upload them on the VLE in the Student Help Center in the relevant section. So the short answer is that yes, the presentation slides will be shared. Next question. How can we know which statistical method to use for our research? For instance, I want to measure the impact of traditional forms of learning compared to formal education. How would I know which tool to use? For instance, can I use ANOVA?
Let us, we want to know which statistical method to use for our research. There is a long process before deciding on your final research project. You will have to pass some research modules and have discussions with your tutors and supervisors, perhaps, depending on the level of your studies. And throughout these conversations, you can pinpoint exactly what it is you are looking for. But if you are looking for differences, if your research question has to ask something that has to do with differences, for example, is something different between two groups, is something different between multiple groups, then you will likely use t-test or ANOVA. T-test and ANOVA look at the differences between means of groups. If your question has to do with differences, you probably will be using a t-test or an ANOVA. If your question has something to do, and all these are quantitative questions, by the way, we're talking about quantitative questions. If your questions has to do with predictions, can I predict this variable from that variable? Can I predict someone's score? Can I build a model that does predictions? Then you will likely need some type of regression or other things that I think are taught in this webinar course. But for sure, there are these two different approaches, two different, let's say, groups of questions. You are either looking for differences or you are looking for predictions. And there are different families of statistics that can be used to answer each one. The other part says, for instance, I want to measure the impact of traditional forms of learning compared to formal education. Yes, that is a question of difference. So you are likely will be using ANOVA if you have more than two groups. If your traditional forms of learning, so let's say you have the ability to go into a school or multiple schools and divide, let's say, 3 classes that do two different types of traditional learning and one, let's say, alternative learning as your control group. I don't know how you will describe your research paradigm, and then measure some kind of performance, some quantitative measure that will be your dependent variable. Let's say you are looking at traditional forms of learning of mathematics. Let's say you will look at the semester grade for that as your dependent variable, and you will have 3 different groups of traditional or combinations of different types of learning. So this is a typical ANOVA question. How would I know which tool, for instance, can I use ANOVA? Yes, you can use ANOVA, I think, as you describe it here, but it's always a best approach to talk to your tutor or supervisor first.
That's very good advice. Yes, you can get a recommendation as to which one to use. Next question. What is the main difference between ANOVA and t-tests?
The main difference between ANOVA and t-test is that t-test compares only two groups of two means and tells us exactly the difference between these two groups of means. But ANOVA, which has as the main product of ANOVA is the F statistic, it takes into consideration the systematic and unsystematic variant between more than two groups. It can be any amount of groups or levels of one categorical variable, because we looked at one-way ANOVA. If you have two different kind of grouping variables, then there are other statistics behind it that are not related with the linear models. But the F statistic of one-way ANOVA takes into consideration the variance that exist between groups, between more than two groups, and the variance that exist within groups. So it's not a simple way of the difference between two groups divided by the standard error. Now we need to calculate a number of residuals and take that into consideration when we get the F statistic in order to avoid type 1 errors.
Okay. So there's a few people who wanted to compliment you on your presentation, Dr. Dragoshis, saying it's very informative. Thank you very
so
much. Much
Yes,
appreciated. So I just wanted to convey that. And on to the final question pertaining to this webinar that we have so far is, which analysis method would you recommend as the best method in examining the relationship between multiple variables?
Oh, well.
Yeah.
Which analysis would I recommend as the best method? Well, it depends. There is no really a best method. The best thing you can do, it's all the pre-processing before going to do the final statistical analysis. First, you need to read a lot. You need to have a great understanding of your data. You need to be able to know what exactly they represent, how were they taken, the population that they are trying to parameterize. You need to have a look and decide what you will do with outliers between different variables, how this will affect your data. And importantly, you need to have a set of questions and hypotheses ready a priori. You don't just go there and start analyzing and throwing things into models, because as we've seen before, models will give you a number, and that's not the idea here. The idea is to know what you are doing as much as possible, and always spending time before going to do an analysis is the best way. So I can only recommend spending as much time as it is allowed on your data set, getting to know it and understand it before you progress to do the final statistical analysis.
Fantastic. An unrelated question, just quickly, how long does the ethics committee take to grant approval? It's not related to this webinar. Neither of us actually know. The best solution is to ask the people who are administrating it for you, send them an email. Another question, Dr. Dragoshis, about the webinar. Considering the importance of R-square in determining the goodness of fit, I wish to find out at what percentage is appropriate to determine the model's goodness of fit.
There is no threshold here. There is no cutoff value. You might have a model that explains 10% of your data, but that will be sufficient depending on your research question. You might have another one that explains 70% and it's also sufficient. So there is no cutoff value here. It depends on the type of data, your research question, the type of food. It depends on many things. That is not really a cutoff value here. It's just a descriptive way that can be used in your specific context.
Excellent. We do not have any more questions now. Let's just wait a couple of, well, okay, there we go. Okay. Again, people thank you for a good presentation. People like how you put it together, Dr. Dragošis. Very positive response to this webinar. So congratulations for that, definitely.
Thank you so much. Thank you to everyone.
And yep, there's no more questions now. So I'm going to end this webinar and we will share the recording hopefully very soon, but it may take up to a month. Thank you very much, everybody, for attending. Thank you, Dr. Dragošis, for an excellent presentation, and we look forward to seeing you at the next webinar, which will be on the 3rd of April, the next in this UU Stats series, and is Seminar 5, Hierarchical Linear Modeling, or HLM. So, thank you very much, everybody, and goodbye.
Thank you so much, Stian. Bye, everyone. Have a nice
Good afternoon. Bye-bye.